So let's say now, is there any change in the screen? Can you see my face?
Yes, sir. We can see your face.
Okay. So the thing is like the recording is also, I'm able to record and we'll be able to talk then in the class, like the live class. So you see, today's the aim of the today's class will be to, up till the yesterday's class, we have like finished the introductory things and what are the like things which we need to use the while designing the things, that what are the parameters which you should consider, and what are the how to design the things, how to design a VLSI circuit, so that we have seen. So now from today's class we will move into the little core things, what I should say. What we have discussed in the yesterday's class, they were also important up till the yesterday's class, but they were all introductory things just to have the familiarity about what the course is about and what you do in the field. But actually now we will start like what is being done and what how to get into the depth of the things. So let's try to understand first of all the MOSFET. Okay. And you may be knowing it already, that what is a MOSFET, but let's try to understand it as related to this course. And in this course, MOSFET plays a very important role, because all the ICs which you are going to fabricate will be based somehow on the this MOSFET. Okay. Or either the classical MOSFET or the some modified forms of the MOSFET like the FinFETs. Okay. So we'll try to understand this MOSFET, because this is like easy to understand compared to the little advanced FETs like FinFETs. So when you try to understand the MOSFET, the very first important thing which comes into the mind is how it operates. So we'll try to understand its operation, and to understand its operation, first of all, we have to understand how the because usually we are going to use the enhancement type of transistor, okay, enhancement CMOS into the ICs. So how the channel is formed into that enhancement type of transistor, and this enhancement type of MOSFET, and to form that channel, what sort of things are required. Okay, some threshold voltage, you hear about the threshold voltage of the MOSFET. So this threshold voltage is like on what factors it depends, and what is the reason for this threshold voltage. So the very first concept we should understand, because you see later on you will study about the current flowing into the circuit and how to control that current. But until unless that the channel is not formed, because in the MOSFETs, the enhancement type of MOSFETs, initially there is no channel. So to form the channel, so initially you have to form the channel somehow, okay, a conducting path, okay, between the source and the drain. So until and unless you are not able to form that, then it is useless to talk about the current. So first thing is like how to form that path, okay, or the channel under the gate region, which is not present initially. So for that we have to understand the threshold voltage. So the aim of this today's lecture is basically to understand the threshold voltage, how the threshold voltage is comes into the picture, and on what factors it is dependent upon, and how you can control it. Okay. So I'll try to cover all the things if time permits for today's class. But if not, then we will divide this particular section of this particular section of the unit into two classes probably. Okay, if we run short of time. Okay, so let's start to understand the threshold voltage. We will start with PN junction. Okay, so we'll see the PN junction once again. You are very much familiar with the PN junction, but let's try to understand it with the help of what is called the energy band diagrams. And we'll see the energy band diagrams not only for the semiconductors, but for various metals, semi-metals, and insulators as well. And this will help us to understand the MOSFET structure. Okay, how the basically we want to understand the threshold voltage, the built up of the threshold voltage. So first we have to see the MOSFET structure, and then from this MOSFET structure we will see that how much charge is how much depletion region is formed in the gate region, and then how many what is the amount of the immobile ions present there, because this all are required to calculate the threshold voltage. Okay, so keep in mind that the aim of the today's class is to calculate the components of the threshold voltage. Okay, what is the threshold voltage equation is, and on what factors it depends. So the whole study, whatever we are going to do, will be for this particular thing. Okay, so keeping in this mind, let's say start. And later on, I mean, in the first few slides, you may feel that the things are like you are not able to understand them sometimes, and people probably they are not connected with what we are going to do. But actually, they are connected, and you will find it like how they are connected at the end of the class somewhere. Okay, in the last few slides, you will be able to connect all the things. Okay, so let's start with the PN junction. Okay, and this all I have told you, because you should be like, nah, you should listen this particular things attentively. So that's what the aim is, to tell you about that, how we are going to flow in this today's class. And there may be some mistakes in the slides also, because I have observed there are some mistakes, but just ignore that. While speaking the things, I'll clarify them. Okay, and if you have doubt, you can ask me. Some slight mistakes may be there in some of the slides. So you see, let's start with the silicon. So if we just want to understand the formation of the PN junction, then the very first thing which we have to start is start with the silicon. So in the intrinsic silicon, if we take, so what we do the doping. Okay, so to form the doping, I mean, to do the dope, we do doping to form the N-type material and the P-type material. Okay, in the same like silicon section. So we take a silicon bar. In that silicon bar, let's say if we dope it with the trivalent impurities like boron, gallium, okay, then it will form your this P-type material. Whereas if you dope it with pentavalent impurities like arsenic, okay, then it will form like this N-type material. So you have like in this substrate, you have P-type material and N-type material. By doping, you make this material. So in this slide only, you can see that it is like P-type material is formed and the N-type material is formed. Okay, so once this material, this PN junction is formed, then what happens? So initially the PN junction looks like something like this. So initially there will like two in the same junction you have formed in the same material, you have doped it with different materials, and then you formed a PN junction. So you know the symbol of the PN junction, and the important thing is like initially in the first this diagram you can see that this PN junction is formed. Okay, there are free electrons and free holes. Now they are like allowed to diffuse, or whatever they want to do, they are allowed. But after sometime what happen, automatically you don't have to do anything, automatically a balance will reach, and to reach that balance, that holes and electrons will combine with each other, and in the junction, okay, in the junction, or I should say where they are like joining each other, the P layer is joining with the N layer in that particular region, which is called as the junction. There are like some immobile charge carriers, are this ions are exposed. Okay, because the charge carriers which were present there got got diffused with each other, and the ions are exposed. So now when these ions are exposed, see what happens. There is a now on the N side, positive a positive layer of ions is built up, and on the P side a negative layer of ions is built up. Now this layer of ions will restrict further flow of the charge carriers, right? And the electrons will not able to flow directly to the P side and will not be able to diffuse, and similarly the holes cannot be able to diffuse in the N side. Now whatever this layer of ions is formed, this is basically generating, giving rise to electric field, and the direction of the electric field is from positive, I mean, from, if I talk in terms of the material, N type material and P type material, it will direct from N type to P type. Why? Because N type is having positive charge carriers, okay, positive like ions, and this P type is having the negative ions. So that particular region is giving rise to your electric field, and the direction of the electric field will be from, you know that the direction of the electric field is like in the direction in which a positive charge carrier will move, if it's free to move. So obviously the holes will be restricted because of this positive layer of ions. So the direction of the electric field will be from N material to P material. Okay, so that is like important. Now further discussions will be based on this only, that the direction of the electric field will be from N to P. And because of this direction of the electric field, some built-in potential will come up, some potential will arise, and to flow the charges, to drift the charges from one region to another region, now what you have to do, you have to apply some external voltage which is more than this particular electric field. I mean, that particular voltage should overcome this electric field, okay, or the voltage which is which arose because of this electric field, this inbuilt electric field, okay. And that voltage in case of silicon is zero point 0.7 volt, we all of know, all of us know that. In case of germanium it is 0.3, right? So now let's see the same explanation you can understand with the help of energy band diagrams. Energy bands, you already know that in case of materials, you can classify them as a semiconductor, as a metal, or as an insulator, okay, like in the form of like energy bands. So in case of metals, you know that the energy bands are like overlap with each other, है ना? Valence band and the conduction band overlaps with each other, whereas in case of insulators, the gap between the energy gap between the insulator, the conduction band and the valence band is too high. Okay, it is 6 electron volt in case of the best insulator, right, the diamond, as you know, whereas in case of semiconductors it is not that high, but there will be some energy gap between the two bands. Okay, so now you can understand this particular thing with the help of this diagrams. So you see, when you have connected the p-type and n-type material, what actually happens, in the unbiased device when you have not connected any voltage to it. So in that case, what happens, the energy band diagram is like shifts itself to adjust, I mean, to flow, to give rise to the flow of charge carriers. So initially what happens, as soon as you combine them, okay, as soon as the materials are combined with each other, then the p-type material will have, like you see, p-type material, in p-type material holes will be present in the valence band, whereas the electrons will be present in the conduction band in the n-type material, right? Now you see, to diffuse with each other, these two levels should be at the same height, okay. You can consider it as a potential energy. So if they are at the same height, then only the transfer from one layer to the another layer is possible, right? So that is why the levels, the energy levels will like align with each other, so that the flow of charge carriers initially, when it is unbiased, okay, when you have not done anything at that time, is like smooth. But slowly, as soon as that alignment is such that after some time, when the device is like that built-in potential is formed, the layers, the valence band and the conduction band, you can see, okay, they are aligning with each other, whereas because of the difference between these two, the conduction band of the p-type and the conduction band of the n-type, there is a difference between them, and because of that, this potential is built up. Okay, so you see, basically this energy band diagram is explaining you particularly this there is a dotted line in between, vertical dotted line, which is showing you the junction, right? So you see, there will be drift and diffusion. I mean, the drift will be possible because of the external voltage only. The diffusion is possible because of the charge difference. So that is all is happening here, and you can consider it that when the device is unbiased, the diffusion will stop after some time, and to further, I mean, whenever you have to like flow the current, then you have to apply some voltage. So the unbiased condition is there, and you can see that the bands are not smooth. The bands are somewhat at the junction, near the junction, there is a deformation in the bands, or they are bending, okay, in some way. So we will understand that how this band bending is taking place. Okay, this particular phenomenon is called band bending. So we'll understand it. Similarly, I have tried also to show you here that how the reverse bias junction will look like and how a forward bias junction will look like. Okay, so the reverse bias junction, and the forward bias junction. In the reverse bias junction, you increase the barrier height again, or the difference between the energy levels between the n-type material and the p-type material, whereas in the forward bias region you reduce that. Okay, and you see why I'm explaining you this, because in the book, I mean the book which I have given you as the textbook, you will see this all explanation in form of energy bands. So that is why this understanding this particular things are important, because if you refer the book and if you'll directly go through the formulas and will learn the, I mean will remember the things in that way, probably you can do that, okay, call it quantitatively. But to understand, I mean in the book you will find is all the explanation related to the energy band diagrams. So if you try to understand and if you're not clear, I mean in clear in those concepts, so you may find it difficult a little bit. So that's why I'm trying to explain you the things. Okay, otherwise if you are like familiar with this thing, then it is not a problem. This is all like fundamental things which you might have studied in your class 12th as well. So to understand this level, I mean this particular energy bands, we require some of the things which you already know, which is like Fermi level. So Fermi level is nothing but a sort of a level, a hypothetical level, which is considered there in these energy bands. Whatever we are talking is all hypothetical. They are not actually present. Okay, we are just talking that these are the present energy levels in which the electrons will reside, and like this is happening. Okay, so the Fermi level is a sort of hypothetical band which have the probability of like 50%. I mean, it is like it is having the probability of 50% probability of occupied at a certain absolute temperature. If I talk about, so if it is an absolute temperature, half of the energy levels will be in the conduction band and half will be in the valence band. But at a certain temperature as well, if you talk about, so the Fermi level will shift accordingly to just maintain this 50% probability. Okay, because at certain other temperature the electrons from the valence band will move on to the conduction band. Okay, at absolute temperature, at absolute zero, I mean at absolute zero, what will happen? There will be no, this conduction band will be completely empty, okay, for any material. So the Fermi level will lie exactly in between. But as the temperature is increased, or because of another phenomena such as doping, this Fermi level will shift, okay, towards either the valence band or the conduction band. I'm talking in case of semiconductors. Okay, so it will shift in either towards the conduction band or the valence band, depending upon the doping and the temperature. Okay, so this is what the Fermi level is about, and you will require this Fermi level, okay, the concept of Fermi level later on. And this Fermi level depends upon, as I have already told you, it depends upon the temperature, it depends upon the impurities, it depends upon the material itself. So the chemical potential of the material, what is the chemical potential of the material, and it depends upon the density of the states. Okay, density of the states, I mean how much denser like the energy levels present in the material. So the density of the states is also matters here. So these are the things on which this particular Fermi level depends. And apart from that, I have also discussed about band bending. So I'll show you that band bending for further some other materials as well, and we will use it later on in our discussion. So this band bending is nothing but it refers to the changes in the electronic structure, whatever this electronic structure is changing, okay, at near the junction. And this happens because of some reasons why this band bending takes place actually. Okay, this band bending actually takes place because near the surface, okay, in the depth of the material, if you'll see, there will be no band bending. The bands will be like parallel and smooth, but near the surface there will be a, near the junction I should say, or the surface, there will be little band bending. And this band bending is because of the imbalance of the charge. I mean there is like in the material there should always be charge neutrality, but at the surface the charge neutrality is not there. Okay, there is imbalance in that charge neutrality near the surfaces. So that is what the reason of band bending. Okay, and why this charge imbalance is there? Because you see, the charge imbalance word itself tell you that charge imbalance means that the amount, the number of, let's say on near the surface there are some atoms. So at the topmost layer, below the topmost layer there are another layer of atoms. So the charge carriers, the covalent bonds, they can form easily. But above that layer, above the topmost layer, there will be no atoms to form the covalent bonds. So you see, because of that, what is happening near the surface, there is unequal number of electrons present. So because of this unequal number of electrons present across the surface, okay, across the surface layer, so because of that, this imbalance occurs and there is no charge neutrality in that region, and because of that, this particular band bending takes place near the surface region, okay, near the surfaces or near the junctions. Whenever you connect two materials, uh, either it is a p-type material or n-type material, or metal with the p-type or any other semiconductor. So in any case, whenever you connect two materials, then this fabricate them together, then in that case what happens, this bend bendings always take place, and this bend bending plays a very important role in, like, whenever you are doing, whenever you are making a new device, okay, whenever you are designing a new device or studying them for any purpose. So then the concept of this bend bending is very important to understand. And the reason of this bend bending, in short, if you'll try to understand, because of all this whatever I have told you, electric field is generated, okay, and that is why I have explained you the electric field. So a electric field is generated, and that electric field actually gives rise to this bend bending, okay, so you can understand in short. And the bending of the bends will be in the direction of the electric field, right? So in the previous slide also, if you will see, the direction of the electric field was from n-type material to the p-type material, and so the bends were moved upward in the direction of the, they were shifted in the direction of the electric field. So the direction of the electric field was from n-type material to p-type material, so therefore the bends were bending upward, okay, you can see. So whenever you are moving in the direction of the electric field, and if you find two different materials, so the n-type material will be at the lower level, whereas the p-type material will be at the little higher level. So there will be a at the junction, at the boundary of these two materials, there will be the transition will not be smooth, there will be little shift in the energy levels, okay, so that is what we have to show, okay. So this is what about it, and now you can see the level of this Fermi level in different materials as well. So the Fermi level in different materials, if you just see, so in metals it is like in this diagram you can see that the lower diagrams are dark, and the lower these regions are made dark, whereas the upper regions are made white. So what are these regions? So these regions are, like, the lower regions are your valence bands, whereas the upper regions are your conduction band. So in the metal, you know that the valence band and conduction bands are overlapping with each other, whereas some of the this conduction bands are empty in itself completely. So if you see the structure of some of the materials, if you see the atomic number and accordingly fill them up in the electronic structure, so you will see that some of the layers are, like, some of the energy levels are empty there. Whereas in the semi-metals are the metals which are in between the semiconductors and metals. So the examples are like your arsenic, antimony, okay, tin. So these are the examples of your the semi-metals. And p-type material we already know, intrinsic material we already know. So what happens in p-type and n-type material, you can easily see from this diagram. In intrinsic material, the Fermi level will be exactly in between. So this is what I was telling you in the last slide. Whereas in case of p-type material, the Fermi level is shifted towards the p side. Because of what? Because of the doping. So as you have doped them, so what will happen? The probability of finding the electron above it and below it will be like 50, it should be 50%. So this is like 50% level. So you see what is happening, the number of charge carriers as is increased in the valence band, so the probability will shift like downward. So the Fermi level will shift accordingly. So in a p-type material it shifts downward near the valence band, whereas in the n-type material it shifts towards the conduction band, okay, because more number of electrons will be present there. So to balance this particular thing, to make the 50% probability, they will shift little higher side. And in the insulator again, they lie exactly in between, but the gap between the conduction band and the insulation valence band is too large, okay. So this diagram was on the y-axis I have taken the energy, okay, the Fermi level, this energy level, and on the x-axis it is the density of the states. So how much denser the number of energy states, how many number of energy states are actually present in the material. So that is what, if higher number of energy states are present, So that is what happens. So this diagram was about that, right? Let's move on to the another thing. So this is like, again, in case of PN junction, what happens? There is a reverse bias. If you apply a forward voltage, then the barrier height, the barrier voltage is overcome, and the amount of electrons present, or the width of the charge barrier, this yes, here this barrier, okay, will decrease in case of forward bias, whereas the width of the barrier will increase in case of your reverse bias. So this is what we already know, so no need to discuss this particular thing, but this particular things we will use later on when we will discuss the the MOSFET device. Now let's come to the structure of the MOSFET, and then from this structure we will we will move on to the derivation of our threshold voltage. So what is threshold voltage, and on what factors it depends, right? So you see, the structure of your MOSFET is something like this. So the first diagram, this diagram is your three-dimensional diagram. So in this three-dimensional diagram, you can see that you have certain two regions which are named as source and drain. The good thing with these MOSFETs is that the source and the drain region are interchangeable. It is not like the BJTs that the emitter and the collector regions are defined, and like they cannot be interchanged. Okay, in MOSFETs, the source and the drain regions are interchangeable. It only depends upon like what voltage you are applying. So if you change the voltage polarities, the source and the drain terminal will change accordingly. Whereas in the you can see that in between source and drain there is some gate is formed. So this structure, particularly if I just describe you the structure, then there is a platform which is called as the substrate. Okay, so the substrate we use here is like p type, and it should be of opposite character of like what type of device you make. So if you want to make an n type device, then your substrate should be of p type. Okay, if you want to make a p type device, then your substrate should be of n type. Okay, so the opposite, they should be of opposite conductivity. This charge carrier should be opposite. Why? The reason is because in that case you will be able to form the reverse bias junction between the substrate or the base. This is called the body. This substrate is also called the body or the base. Okay, so you'll be able to easily form the reverse bias between the substrate and the source and the drain region. So that is what the reason is, that we use the opposite type of materials. Okay, now there is a gate terminal. Then this gate terminal is used to control the flow of charge carriers between the source and the drain region. Okay, so this is what the dimension. This is what about the structure of the MOSFET. And between the gate layer and the substrate, there is an oxide layer. Okay, so which is like SiO2. So this oxide layer basically this helps you to control the device as a voltage controlled device, and it will basically form initially as a capacitor, because there is an insulating layer. On the top there is one layer, on at the bottom there is another layer. Okay, two metal layers you can consider. So one on the one top layer, which is like gate terminal, that is a conductive plate, so it is obviously a metal. So you will apply some voltage there, and because of that voltage you will be able to attract some charge carriers either directly from the substrate or from the source or the drain region. Okay, source region basically. So this is what the purpose of this gate terminal is. So the first diagram was the three-dimensional diagram. The single line diagram, if you see the front view, so then it looks like the diagram B, and the symbol for the MOSFET for the NMOS is this. Okay, so this is the symbol for your NMOS, the diagram C, right? So this is what the structure is. Now let's try to understand that if suppose I just remove those source and drain region, and I just consider the region under the gate. Okay, then this region under the gate is like, let's consider it as a two terminal device. Okay, and this two terminal device is nothing but the same structure what you have seen earlier. And why I have shown you that structure earlier, I could have shown you this structure directly, and in the book also you will start the discussion with this. In the book the discussion is started with this particular diagram. Okay, so don't get confused. I mean, you should know that actually you are discussing, you want to discuss the things for that MOSFET, but to start with the things at the very basic level, or at the very simple level, the discussion started from this particular two terminal MOS structure. Okay, and sometimes we miss that like how they are connected, because this is what problem I faced in the earlier semester when I taught that people are not able to understand this connectivity, like why these things are explained there. Okay, so just have the look into this two terminal structure. So this two terminal structure, as I have told you, we have removed the source and the drain region, and this gate terminal we are considering, and the region under the gate region. Okay, so you see what is happening now. So and in this particular case, initially I am not applying any voltage as well. Okay, whatever voltage we will apply on the gate terminal corresponding to the substrate terminal. Okay, here presently, but later on those all voltages will be with respect to the source. So these are the various layers, and in these layers, if there is a semiconductor, then you easily know that there is a mass action law which it follows, so which is n into p is equal to ni square. So the number of charge carriers is equal to the product of this charge carriers will be equal to the square of the intrinsic charge concentration. So ni is the intrinsic charge concentration. Okay, so then from this particular equation, if you want to find the amount of charge carriers, majority charge carriers, so the majority charge carriers in case of p type material will be np0, which you can find by this equation, ni0 by na. So na is the doping concentration. Okay, so if you dope it the material with trivalent impurity, then it is a acceptor type of impurity. Okay, so this is what it is. Similarly, if it is a n type material, then the equations will be for nn. So it is like nd you will use here in the denominator, ni square upon nd. So the number of electrons present. So this is what the two terminal structure, and you can easily know that how many number of charge carriers will be present from this equation. So first aim is to find the number of charge carriers. Okay, so the amount of charge carriers which you know will be like what will be the density of the electrons, so that we know. Now let's move on to the energy band diagram of this p-type silicon. So why I'm using p-type silicon? Because the substrate is of your p-type. Okay, that is why in the previous slide also we have considered the np0 for the this p-type material. So the energy band diagram of this material is like something like this. Okay, so you can consider it as the inverted potential energy diagram. So if you consider about the potential energy in the physical level, so you see, you consider that how much away how at what height you are actually from the surface, from the ground. So if you are at more height, then you say that the potential energy is high or is more. Okay, if you are near to the ground, then the potential energy is low. So similarly, in case of materials, what we do, we consider the free space as at the zero level, let's say. Okay, and all the levels will be measured with respect to that. So the material which is away, which is more further away from the free space, will have more potential energy. Okay, similarly on that line you can understand with it with this analogy particularly. Okay, because all the materials will try to, all the electrons will try to escape in the atmosphere, in the free space. Similarly, I mean, it is similar to what, I mean, if you throw object, or if you just increase the height of any object, then what it will try to do, it will fall near to the surface. Okay, it will try to fall towards the surface. So the same thing is here as well. So that is why I have told you that just assume it as like inverted potential energy diagram. Okay, so you see what this diagram is actually showing you is like free space, and in the p-type material there will be this conduction band, there is valence band, and this Fermi level band, and the intrinsic this Fermi level band. So intrinsic Fermi level band is like when the material was intrinsic, so that dashed line is showing that particular level. But as you have doped it with p-type material, then what is happening, the Fermi level is actually shifted towards the valence band. Now, the difference between these levels is termed as your Fermi potential. Okay, so in the first slide, you can, I mean, in the first, this particular C, you can see that the difference between the conduction band, whatever potential or whatever the energy difference between the conduction band and the free space, you call it as your electron affinity, because that much amount of energy will be Q into the Xi. Okay, so that is like denotion for your Q Xi is your electron affinity. So the amount of energy, how you define the electron affinity? It is the amount of energy which will be required to remove the electron from the conduction band to the free space. Okay, so you see this qx, this q sign, whereas the difference between the this other energy levels, the valence band and the conduction band, you can easily find the difference as ec minus ev. And this band gap, I mean, if you just write this phi, okay, so this phi notation is also used usually, and this phi notation is nothing but your Fermi potential.